Welcome to the fourth episode of the FORCESPRO demo series on path tracking control. In this video, we will show how to run the code for generating the FORCESPRO SQP Fast solver for path tracking applications. We are still in the path tracking high-level example folder, but now we are looking into the path tracking SQP Fast script. In order to generate the SQP Fast solver, we first need to generate and simulate the SQP general solver. This way, we will obtain the cache problem data needed for tuning of the SQP Fast solver. Therefore, we run the generate path tracking solver function described in detail in the previous video. Notice that the last two arguments of this function are a user fast solver boolean indicating if you are using the SQP Fast solver, and the float type string indicating if you are using single or double precision. Based on the value of the used fast solver, the forces get default options will set up the code options for either the SQP NLP Fast or SQP NLP solver. Let's now go back to the main script. As we can see here, for the purposes of the SQP general solver, we will disable used fast solver and work in double precision in order to obtain the most accurate cache solutions. By running generate path tracking solver, we get the model and code options struct needed for generating the FORCESPRO NLP solver. Once the SQP general solver has been generated and downloaded, we can simulate the model and collect the cache problem data. We can now turn our attention towards the SQP Fast solver. We again run the generate path tracking solver function, but this time we enable use fast solver and use single precision to get the most lightweighted solver. This provides us with model and code options struct. As a last step, we need to obtain and set up the tuning options for the SQP Fast solver. This is achieved by running the forces auto-tune options with cache problem data as input. In addition, we set the tuning goal to speed, adjust the tuning seed and the number of tuning iterations in order to make tuning deterministic, and declare all control outputs for validation. Note that the alternative tuning goal would be control, which provides tuning for best matching of the control performance of the cache solutions. Once the tuning option struct is completed, we are ready to generate a tuned SQP Fast solver by running forces generate SQP Fast solver. We can then simulate the model, as well as obtain and plot the results. Let us now run this script and see how the tuned SQP Fast solver is generated in real time. The SQP general solver is now being generated. The SQP general solver has now been generated and downloaded to our host machine, and we start simulating the model. Once the simulation is completed, the cache problem data is stored, and the auto-tuning of the FORCESPRO SQP Fast solver initiates. The solver tuning is completed after 10,000 iterations, as set in the script, taking about 90 seconds on this PC, and the obtained tuning parameters are used for generating the custom SQP Fast solver. The new solver is successfully generated and downloaded to our host PC, upon which the new simulation starts. The simulation is now completed, and we collect and post-process the results. The control performance remains unaffected from switching to the SQP Fast solver. On the other hand, the desktop computation time is reduced by a factor of 2 compared to the SQP general solver. The performance on Infineon Oryx confirms the previous findings. The max computation time, as well as the memory usage, are reduced by a factor of 2 compared to the SQP general solver, which clearly indicates the effectiveness of the custom-tuned SQP Fast method. This completes the code example of this demo for the FORCESPRO SQP Fast solver.